All right, lesson 3.1, concavity, points of inflection, second derivative test. A graph with this shape, it looks like it smiles at you, is called concave up. The slopes are increasing left to right when it's concave up, and the second derivative is greater than or equal to 0, meaning the second derivative is positive. When something is curved the other direction, it looks like a frown. That means the slopes are decreasing left to right, and that the second derivative is negative. When there's a point where the concavity changes, it's called the point of inflection. So not only must the concavity change at that point from concave up to concave down or vice versa, the derivative must also exist at that point. So there can't be a sharp corner or cusp and so on. All right, let's look at the graph. I want to know, looking off a graph, can you tell me concave up, down, or if there's no concavity? So I'm going to use yellow for concave up. So this first part of the graph is concave up. It's like half a smile. This is also concave up right here, as it is a full smile. And then the last part that's concave up is right there. And I'm going to write that down. Those are the intervals of concavity up. So that's -2 to -1. That's also 1 to 3. And that's also 4 to 5. Intervals of which it's concave down, I'm going to highlight that as well with a different color. This is concave down, and this is concave down. So intervals of concave down looks like a frown. That goes from -1 to 1, and it goes from 5 to 6. Now I'm going to have another color where there's no concavity. A line has no concavity. So this part here has no concavity, and there's a line here too that also has no concavity. So from 3 to 4 has no concavity, and from 6 to 7 has no concavity. And then it says, where are the points of inflection? Where does the concavity change? And the derivative must exist there. So where does the color change? So the concavity changes here, but the derivative does not exist because it's a sharp corner. We couldn't draw a tangent line that connects both colors. So there's no point of inflection here because the derivative doesn't exist at a sharp corner. Here, the colors change and the derivative exists there. That's good. So at 1, 1, there's a point of inflection. There's no point of inflection here because we're going from concave up to no concavity. And there's no point of inflection here. Again, we're going from no concavity to concave up. But there is one right here. So the derivative exists and the concavity changes. So 5, 1 is the other point of inflection. Turn the page. So we're now going to find concavity algebraically, not on a graph. And we need the second derivative to find concavity. So in order to find the second derivative, I needed the first derivative first. So the first derivative is 4x cubed plus 3x squared minus 6x. Then the second derivative, that's 12x squared 6x minus 6. And then you're going to make it equal to 0 and solve it. So it's probably smart to reduce it down first. So that's 2x squared plus x minus 1. And then we need the skill to know how to factor this. So if I factor this, I'm going to just guess and check. 2x times x is 2x squared. For -1, it's 1 times 1. And then I need to know which one should be positive and which one should be negative, so it adds up to positive 1. So for this to work, it needs to be 2x minus 1 and x plus 1. So if I find the middle term, that's -x plus 2x, it gives me positive 1x. So those are the factors. The first factor gives me the answer positive 1/2, and the second factor gives me the answer -1. Now, we're going to draw a number line, and we're going to label it. So -1 and 1/2 we'll put on that number line, and then I'm going to plug in a number in each interval into the second derivative. So if I plug in -2, the first factor is negative. -2 plus 1 is also negative. So a negative times a negative gives you a positive concavity. Plug in a number between -1 and 1/2. 0 is probably your best one. So if I plug in 0, it's a negative. Plug in 0, it's a positive. So a negative times a positive is negative. Then plug in a number bigger than a half, like 10 or something. Plug in 10, and you can see it's a positive times a positive, which is positive. That means this is concave up, where the second derivative is positive. So from negative infinity up to negative 1 and 1/2 to infinity, it is concave up. It's concave down where the second derivative is negative. That goes negative 1 to 1/2. And then the point of inflection. So at negative 1, we have a point of inflection because the concavity changes. If I plug negative 1 into here, I get the answer. Let me just do this quick. I get 1, take away 1, negative 3 plus 1. Can you do that? I'm like pulling up the answer key. So I don't have to think through it as much. So the answer is, so it's negative 2. And the other point of inflection is at 1/2. Then you have to go back to the function, plug in a half for x, and you'd get the answer 7/16. All right, last one for doing this in terms of concavity, and then we're going to talk about the second derivative test. So here we have x squared plus 1 over x squared take away 4, and we have the second derivative. So first of all, I need to know the domain restrictions. So the two numbers x cannot be are positive 2 and negative 2 because it makes the denominator 0. Next, I look at the second derivative and look at the numerator, and I solve it. Now, if I try to solve that, there are no real solutions. So when you divide by 10 and get x squared by itself, you end up with the square root of a negative number, not real. There are no solutions here that would make that 0. So those are my only numbers that I care about, negative 2 and positive 2. And then into the second derivative, if you plugged in negative 1, you would end up with a positive over a negative. If I plugged in a number between negative 2 and 2, like 0, you would end up with a, let me try that again. If you plugged in negative 3, you would end up with a positive over a positive, because negative 3 squared is 9, take away 4, so that's a positive. This is going to be negative. When you plug in 0, you'll end up with a positive divided by negative. And if you plug in a number bigger than 2, like 3, it's a positive divided by a positive, which is positive. So we just learned that it's concave up from negative infinity to negative 2, and from 2 to infinity. It's concave down from negative 2 to 2. Done. And then there are no points of inflection because the concavity changes at asymptotes, at the restrictions. So what x cannot equal cannot be a point. So there are no points of inflection. All right, number 7. You can use what's called the second derivative test for relative extrema. So if I want to find maximums and minimums, there's another way to find maxes and minimums, and that's using the second derivative. So let me show you how that works. So if I want to find the maximums and minimums, I'm going to take the derivative, and then I'm going to make it equal to 0. So there I do it. I'm going to factor out a negative 12x. So I have x squared minus 1. And then I'm going to solve this, or keep factoring it. That's x plus 1, x minus 1, a difference of squares. So I factor it. Now, negative 12x gives me the 0, 0. This is negative 1, and this is positive 1. All right, that's like what we did before. But now we're going to do the second derivative. So the second derivative is negative 36x squared plus 12. And then I take the critical numbers and plug them into the second derivative and see if the answer is positive or negative. If I plug in 0, the answer is positive, which means it's concave up, which means this is a minimum. If I take the second derivative and plug in negative 1 squared is 1. And then it's negative 36 plus 12, which is negative. That's a max when it's concave down. And then one more time, plug in positive 1. And again, it's a negative plus 12, so it's a negative. Again, it's a maximum because it's concave down. So concave up creates a minimum. Concave down creates a maximum. And so I know my relative minimum is at 0. And then the y-coordinate, if you plug in 0 here, is 0. And then we have maxes. So both positive and negative 1 are maxes. If I plug in positive 1 or negative 1, the answer is 3. So at 1, 3 and negative 1, 3, we have minimums and maximums using what's called the second derivative test. So again, you take the first derivative equal to 0, find your critical numbers, take the second derivative, plug into the second derivative to see if the answer is positive or negative, and that tells you if it's a minimum or maximum, and then plug in to find the y-coordinate. Last question, number 8. G at x is a function so that you have these values and find the x values of the maximum and minimum. All right, so when a derivative is equal to 0, that number is called a critical number. So negative 3 is a critical number because when you plug it in, it gives you 0 for an answer. Negative 1 is a critical number. 0 is a critical number. And 2 is a critical number. Because when you plug it into the first derivative, the answer is 0. That's the definition of a critical number. Then the second derivative, I want to know the second derivative at negative 3. The answer is positive. That's concave up. That means it's a minimum at x equals negative 3. That's how it's going to work. The next one, the second derivative at negative 1 is a negative answer. That means it's concave down. So we have a maximum at x equals negative 1. At 0, the answer is 0. That means we don't have a max or min there because it needs to be positive or negative. And the last one is at 2. So the second derivative at 2, the answer is positive. So it's concave up. So we have a minimum at x equals 2. And notice the second derivative at positive 1. This is to fool you. It has to be a critical value to give you a turning point. So it's not a critical number, so it's just there to fool you. All right, Mr. G Math, over and out. Till next time.